Now, connect the particles in 2021. Reasonably okay question, I think. Fairly okay. So you have just a slight variation on your usual one. And normally you have the old free pulley with the free weight on that side. This time you've just nothing on that side, and a pan as well, which just slight complexion. So you have to show K bigger than 2. System is released from rest. The pan moves upwards. So it's kind of a hint already. If you know, you're told that has to move upwards, then you know that your acceleration has to be bigger than 0. And something is moving, and that'll probably lead to your inequality there. So let's have a look at it. And again, your diagram is kind of everything with these ones. C, and here's your pan. What is the mass of these guys? So C is Km, mass of Km, and that's probably M, isn't it? Yeah, and you're told that the pan is weightless or light, and that's basically code for you can assume it's weightless. Okay, yeah, that's Km, block D. Okay, yeah, system released from a scale pan moves upwards. Okay, you're told that moves upwards. Sometimes you're just told solve the thing, and in theory you could have total balance. You could find the acceleration at 0. You now know this time you've been told it's moving upwards, so that's a hint as to what kind of inequality you might be able to get later. Well, but the easiest ones are put in the masses. You always have a tension. You have always have a tension here. You've got 2 now with this lad. And then that has kmg. Now the acceleration, so let's say that moves upwards. That means this guy is going to move downwards. So if that's got acceleration of a, then that one will be moving up with 2a. Now the reason for that, and this is just something to remember, and you might remember in your old one with the movable pulley and the free weights, that this one has, okay, so if that's A, that's B, then this one has the average acceleration of the 2 to either side of it. And this is kind of similar here. That's kind of getting the average of that one to that side, and it's got nothing to the other side. So it's getting the average of A plus 0 over 2A plus 0 over 2. So it's basically half it. So that will move at half the acceleration of this. And the reason for it really is because when that moves up, if that moves up by 2 meters, let's say, or 2 units, 2 meters, then that means because there's 2 kind of strings here, 1 meter will have to be released down this side and 1 meter will be released down that side. So that the string is of constant length. So for every 2 meters that moves up, that can only move down 1 meter. It's half as fast, if you know what I mean, because it has to spread it across 2. So that goes up 2 meters, that rope is released down 1 meter, and that rope is released down 1 meter. So that's the reason for the lower acceleration. Okay, so then just do your Newton's laws on each one of those lads. Okay, so for D, you know it's moving up, so it's T minus mg is equal to m2a. And C is 2t in the odds of the 2 times, well, it's moving down, so let's do our kmg minus 2t is equal to kma. Alright, so let's go through that, and we get t minus mg is equal to 2ma, and that's kmg minus 2t equals kma. Okay, we need to solve, we're going to solve for acceleration. So let's get rid of the tension, let's say. So we'll multiply that guy by 2. So 2t minus 2mg is equal to 4ma. Okay, so add these two and the tensions will cancel. So it's mg into k minus 2 is equal to ma into k plus 4. All right, so masses cancelling, and you get A is equal to G k minus 2 over k plus 4. So it's interesting always to see the acceleration tends to be a factor of G. So it's G times this over this. So that it's that factor of G. So if k was equal to 2, then there would be no acceleration. But you know that there has to be an acceleration. So that means A is bigger than 0 because you're told it does move upwards, which means there has to be some form of acceleration, however small. That means that G k minus 2 over k plus 4 has to be bigger than or equal to 0, which means that this factor, the bit above the line, has to be bigger than 0, which means has to be bigger than 2. It's important because the bit under the line, if you like, you're cross multiplying, you can cross multiply that, and it's k plus 4 multiplied by 0, 0. So you get G times that, bigger than 0, and then you can divide that if you like, that goes to 0 as well, and you're just left with k minus 2 bigger than 0. So k must be bigger than 2, which is the first thing we're asked to do. Find the tension in the string. Well, let's pop it into one of these lads. So T minus mg is equal to 2ma. Okay, so we have acceleration then. We have this lad nice and clean. So T minus mg, well, T is equal to, let's say, mg plus 2m j k minus 2 over k plus 4. And we can take mg out of that. So it's mg into 1 plus twice this lad. And we can simplify that further to get tension. You would just put that k plus 4 over k plus 4 and get that. Find the terms of the reaction between D and the scale pan. So that's the interesting bit. So now we're looking at the scale pan here. And this is probably the interesting bit where you're looking at the scale pan in more detail. Now, well, what's happening? Well, the reaction force is always perpendicular to the surface. So let's call that R. You have mg down. And actually, it might be useful to just finish out that T there. mg into, okay, k plus 4 plus 2k minus 4. Okay, bit of cancellation, nice one. So the 4's cancel, and we get T is equal to mg into 3k over k plus 4. All right. Okay, grand. Now, this lad here, so find the terms of K and M, the reaction between D and the scale pan. We know that that moves up with acceleration 2a. Okay, so we know that, so that means that R minus 2 minus mg is equal to 2a m. So R is equal to mg plus 2ma. Right, which looks remarkably similar to this, and in fact it is. So if you look up here, so tension is equal to mg plus 2ma, basically is the result we got up here, and we're getting the same for the reaction force. And this is the thing, in the solutions they they come up to that as well, but there's absolutely no mention, of course, of the similarity. So we get the same answer there, and but they just leave it there. And I think it's an important result, and it's kind of something that you might be asked in the future. So really, what it's kind of saying is that tension is very linked to the reaction force. They come out as the same. But really, this thing, What that's saying is your reaction force is bigger than the weight. So, and this is something to notice anytime you're in a lift. If you're in a lift and the lift is going downwards, it starts accelerating downwards, particularly if it starts accelerating quickly. So this is a human and you have your feet here and you'll feel the reaction force. And if you're standing on anything, you feel the reaction force between your feet and the ground. If you're in a lift and it starts accelerating downwards, you'll feel a certain weightlessness as it accelerates. Next time you're in a lift, notice for that, when the lift starts to take off. So you'll feel lighter. If that starts to increase, the bigger that acceleration is, the lighter you'll feel. In the extreme case, if A was equal to G, if you were accelerating at 10 meters per second squared, you would feel completely weightless. Your feet would actually, the reaction force would actually be zero because you would actually start floating then. All right, so you can feel that in a lift. The opposite is true if you're going up and you start accelerating up, then you feel your reaction force is much higher. You start feel a lot heavier when the acceleration goes up, and the higher the acceleration, the more heavier you feel, and that's given out by this. So if you're going upwards, the reaction force you're feeling is more than just your weight. That would be your weight, but it's also then this acceleration factor added on as well, and that's really the tension that's pulling the lift up is causing that. Totally overlooked by the solutions, but you know, you might, something useful to notice. Okay, a wedge question. F in terms of M and forces removed. Yeah, so find the acceleration. So it's a pretty standard one, apart from the fact that you have your pretty standard wedge, apart from the fact that you have this force F, which is blocking it initially. So you have your mass, 30-degree wedge, you have your reaction, mg, and so your wedge will try to move that way. As that slides down, it'll try to move that way, but that force is blocking it from moving. So separate diagrams, that'll be mg, that'll be reaction, and the wedge then sees this reaction force coming in here. So, and you can resolve that in terms of this or sine 30 and a reaction into the wedge then, or cos 30. It'll have that force acting on it, and of course everything has an mg and its weight is 4m. Yeah, so that's 4mg, and that'll have a corresponding reaction S. Now we're never really too worried about this reaction S. Doesn't tend to be particularly useful in the equations. In the equations, we're really concerned with the internal reaction there between the particle and the wedge, and A and F. So it's kind of a three variable problem. So you apply your three equations. Standard way, I think that's probably no different to the usual wedge question. So I don't think there's an awful lot new in that one. So your wedge, you have this r sine theta minus f is equal to 4m. What's the acceleration of the wedge? Acceleration q. And in this case, like the initial case, q is going to be 0, but let's just do the general anyway. Particle downwards. Okay, so the other one is the acceleration of the particle, and that's p, and q is this guy with 30 degrees between them, isn't it? Yeah. So that is q cos 30, and that will be q sine 30. And what's the 30 angle? Well, it's 1 root 3, 2. Yeah, okay. So the particle down the slope, it's smooth, so it'll be just what's gone down the slope. It has mg sine 30 minus nothing, so will be equal to mass by the acceleration. So it's p minus q cos 30, which is, so q root 3 over 2. And particle inwards will be mg cos 30 minus r will be equal to mq over 2. Okay, so you have your three equations. So three equations, and it's useful to remember that they're in R, A, and F. Three equations, three unknowns, and you just solve for those, which is reasonably okay. So the first one, these will be 0, and it'll be fairly trivial to find F in terms of M. So that'll be fairly trivial, F in terms of M. You'll just be able to find F in terms of R, and then substitute it in down here. Okay, and then the last one, you're just solving the three equations there. So reasonably handy connected particles question.